What do you think? Do you think I should stop and check? I mean, what do you think? You think it's doing it? Okay, there's a way that I make this go away, though. Oh, look at this. Now do you think it's recording?
Sure.
Hi. Well, the video panel was my little picture. Oh, see, that's still showing. Okay, so we got rid of that. It's like you can do a meeting like with people all over and they all log in and then you can record it. You know, we're in a meeting right now. Did you know that? Maybe it'll just have sound. Oh, I'm trying to hide that thing so you can see it better. Well, that didn't help much. Oh. I just live here. All right, I'm going to open this because you've all got it done now, right? I'm thinking 26. 4 to 5.6. Sorry, the truck is really big. Do you understand that this bond is in front of that bond? Do you see the perspective in the drawing? Okay. Just checking. All right, I still only have 25 though. Is there one more person? Or can I not add or subtract or? Okay, all right, we're up to 26. Okay. Oh, I hope it's B. Okay. So these two are your bridgeheads. Okay, so how many carbons are in the whole framework? 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm getting 9. So that means your base name is no name. So it's going to be bicyclo, no name. Okay, and what goes in the square brackets? Okay, you count how many carbons are in each deal. This one's going to have 1, 2, 3, 4. This one has 1. And this one has 2. And you put them in 1, 2, 4 or 4, 2, 1? 4, 2, 1. I told you I had nothing to do with any of those rules. Okay, and you need to use the square brackets. Don't use parentheses. Don't use commas. Use the dots between those numbers. Just weird. Okay, they're like their own little entity. Okay, so that was B. Woohoo. Okay. Okay, so we're going to start talking about conformational analysis today. Conformations are spatial arrangements of a molecule that are generated by rotating around single bonds. Okay, and there are going to be differences in energy, and that is what is basically conformational analysis. It'll make more sense when you have a molecule to look at. Do you have that slide? Y'all are writing madly. There's a lot of blanks. There's only 2 things. Oh, okay. You want every individual word. Okay. Y'all should be writing super fast now. I really hope it's recording. If it's not recording, I'm going to feel really stupid later. Okay. All right. Are we up? All right. All right. So this is ethane. Ethane has how many carbons? 2. Okay. So here is a model of ethane, and that's a picture of the model that I'm holding on the slide. Okay. So if you remember, I've already mentioned that you can rotate around single bond. Okay. I'm rotating around the single bond. Okay. As you go around the bond, okay, if you go all the way in a complete circle, tell me degree. 360. Okay, just checking. All right, make sure we're all on the same page. It's 360. Do you see that there are basically an infinite number of positions all the way around, right? But there are 2 extremes where they're all lined up. This hydrogen in front of this one in front of this one in front of that one. Or they're all perfectly every other one. See that? Okay. The one that's up there on that slide is the one where they're all one in front of the other. That is called the eclipsed conformation of ethane. Eclipse. Okay? One in front of the other. That makes sense? You know, the moon going in front of the sun. Okay. Okay. That's the eclipse. Okay, that's a whole eclipse thing. So this is looking at it this way, and this one is looking at it that way. All right, so here's the other one. This is the staggered one. Okay, and I'll try to make it exactly match that one. Okay, so you'll see that I have, it's every other one. When you look down the CC bond, do you see that you see every one of the hydrogens except the one I'm holding? Okay, you see every one of the hydrogens. Okay, that's staggered. They're every other one. Make sense? Okay. And that's the pictures of them up there. Okay, this is the first picture. Okay, yep. And this is the second picture, the perspective. All right, with me so far? Okay, and are you going, okay. Okay, this is how we draw them, okay, so that we don't have to draw all that perspective, okay? That would be like really difficult. So these are called Newman projections, okay? And the way they work, let me get a pen here, is this carbon right here that I've made a red dot is the front carbon. That's the front carbon. So you see the front carbon, I'll make this one match that one, has 3 hydrogens. 1, 2, 3. That's these 3 are coming off of that carbon. That's the front carbon. And then this thing in the back, this big green circle, is the back carbon. And these are the 3 hydrogens coming off of it. Every carbon has how many bonds? 4. Where's the 4th bond? It's between the red carbon and the green carbon. Okay? We don't necessarily show that because we're doing a Newman projection. You can only show 2 carbons at a time in a Newman projection. If you want to have a carbon up here, you have to write it in. Okay? But you'll always cite down 1 bond. Okay? It's like I'm citing right down that bond. Okay? Okay, so this is how we draw the staggered one. That's the easy one. The one that's a little trickier to draw is the eclipsed one. Because if you drew it exactly eclipsed, what happens? You can't write the one in the back because the one in the front is covering it up. So what we do is here's the front one, here's the one that's in the back, and we just make it a little bit off by a little bit. Okay, I have a program that has those in them and it puts the white in there. Don't ask me why. But it doesn't matter if you put the hydrogens in the back to the right or if you put them to the left. It doesn't matter. I don't even care if you mix it up. So if you were going to draw, here's your front carbon. Okay, and you're going to draw it, and you put this one here, and this one here, and this one here. I don't care. I don't care which spot. You just want to put it kind of close. Now, what I do care is that those back lines, do you notice they stop at that big circle? They don't go like this. Do you see what's wrong with that? What are we doing to the front carbon? We're giving it 100 bonds that it doesn't have. Okay, so we're gonna erase those puppies. Okay, because I just can't leave it on there. It like bothers me. Terrible. Okay, any questions on the drawing so far? You'll see we're going to be drawing stuff. You're going to be drawing stuff. Okay. Okay, which do you think is more stable? The eclipsed or the staggered conformation? Which one do you think is more stable? What do you think? From your vast knowledge of organic chemistry, do you think it's going to be more stable to be eclipsed? Or do you think it's going to be more stable to be staggered? Staggered. Jessica whispers. Okay, why do you think it's going to be staggered? Because all the hydrogens are what? As far apart from each other as possible. Remember that. Things are arranging themselves to be as far apart from each other as possible, so they got room to grow. Okay, so conformational, in which the torsion angles between the adjacent bonds are other than 60 degrees, are said to have torsional strain. So what we're looking at when we're talking about that angle, oh, hang on. Good gravy. Okay, here we go. Okay, is we're considering, okay, I drew it in green, okay, and now I'm just going to put black. We're looking at this angle. Okay, so it's like this and this are the two sides. Okay, that's why they started drawing the pictures like this, because you could see the angles very easily. Okay, so what is this angle here? What do you think? It's 60 degrees. Because as you go around, okay, you're going to end up with 6 pieces. So it's not just like a split, okay? So if your angles are other than 60 degrees, and basically it's smaller than 60 degrees, then you have torsional strain, okay? I should put less than 60 degrees, okay? So if you look at the eclipsed one, okay, what is this angle here? It's 0, okay? Even though it might look like there's a little one, it's 0, okay? So it's right in front of each other. So if you were even 30 degrees, you would have torsional strain, okay? But the extremes are going to be 0 and 60, okay? Just hang in there. Okay, if the hydrogens are 180 degrees apart from each other, okay? You see how we got that? We're taking this whole deal, okay? That is 180 degrees, okay? So you've got one on the top and one on the bottom. That would be these two. I tell you what, I'm going to make them colored. I'll make them red on my little, oh, that one looks, I guess they're kind of orange red. Okay, so you see that they are 180 degrees from each other. We call that anti. These two hydrogens are anti to each other. Do they have to be up and down? What about these two hydrogens? What are they to each other? They're also anti. Okay? And of course, these two hydrogens are also anti. Okay? Because you know we're going to take away the hydrogens in a minute and put stuff there. Okay? Okay. If they are, here I will change my little deal, like this. Okay? If we are looking at 60 degrees, okay, that is called gauche. G-A-U-C-H-E. It's pronounced gauche. It's not gaucho. Okay, it's gauche. Personally, I don't care how you say it. Just write it down right on your paper. Okay, so everybody seeing that? So between anti and gauche, which one of those do you think would be more stable? If the two groups were anti or the two groups were gauche? Anti is more stable because they are farther apart. Okay? The terms anti and gauche apply to bonds or groups on adjacent carbons. So if I have 5 carbons and I'm looking at a carbon here, okay, it has to be the one next to it. We're not going to say that the carbon 4 down is gauche, okay? It doesn't work that way. It's only ones that are right next. So you're looking at these little Newman projections, okay? And I think it'll help when we do some compounds. Okay, now you already told me that that the eclipsed was higher in energy than the staggered. Okay, what they did, or what we did, is we drew a potential energy diagram. Now, did you do any potential energy diagrams in journal chemistry? Did you talk about like starting material ones with starting materials and products, and if it's exothermic and endothermic? Did you not? And you drew the little scoopy line? All right, well, that's all right. That gives me ideas. Okay, because we're going to be drawing those too later on. All right, so to draw a potential energy diagram, number 1, you need axes, an X and a Y, okay? The next thing you need is this thing to go away like it's supposed to. All right, I'll just move it out of the way, okay? Labels for your axes. The y-axis is called potential energy. So if it's higher in energy, it's higher on our graph. You'll notice that I have no numbers. There's no numbers on that. It's going to be relative. Okay? This is higher in energy than this, so it's up here. Okay? But please don't make them this close on your piece of paper. Like, make it obvious. Okay? All right, this one, which is, that one went away like it was supposed to. Okay, is your x-axis, okay? This is going to be, what we're going to do is we are going to take our compound and we are going to go all the way around all 360 degrees. You can write the degrees, or you can just write degrees of rotation, okay? Like, I'm not always going to show 60, 120, but we're going to show all of the different extremes, okay? Okay, so when we start, you'll notice that the 2 red ones, these will be my 2 red ones, okay? One is in front of the other, we are eclipsed. And then I'm going to take the front carbon and I am going to move it clockwise. Does everybody agree that's what we did? We moved it like that. Okay, so we went from eclipsed to staggered, okay, which is more stable. Staggered, so we're lower in energy, okay? Now, I only have this color just for the sake of that you can tell which one is which, because when I go like this and I make it eclipsed again, it's really exactly the same as this one, isn't it? Okay, so you'll notice that it is the same place in energy as this one, okay? And then we're going to go, boop, we're going to be staggered, And look where we are now. Okay, we're at 180 degrees. Every time we turn it, we're turning it by 60 degrees. Okay, then we're going to go like this, and we are now eclipse. So we go up here, and then we do the last one, and we're going to be we're going to be staggered, and then we're back to where we started. So to do a complete conformational analysis around a CC single bond, you will go all 360 degrees, even if some of them are the same energy levels. Okay, we got 2 energy levels for this one. We have staggered and eclipsed. The difference between them is 12 kilojoules per mole. Not a huge number, but what it means is that at any given time, more of the ethane molecules are going to be staggered than they will be eclipsed. Remember that they are moving. Molecules are moving. Unless they're at absolute zero, molecules are moving, okay? And so what we've done now is we have connected them with a little graph. See how I got that? Okay. It looks kind of like a sine wave. Would you agree? Okay. Okay, now what we're going to do is we're going to put groups on. We're going to change it up a little bit. Okay. Okay, so the compound that gets done the most is butane. Okay. Butane has how many carbons? This is the one that's in your book too. What? It has 4 carbons. Okay, there's butane. And what we're going to do is we're going to cite down carbon 2 and carbon 3. So one of these, get over here, is going to be my front carbon, and one will be my back. Front, back. Okay, so what I'm going to do is I'm going to make what's attached to the front carbon? What's attached to it? 2 hydrogens and a CH3, a methyl. Okay, I'm going to make the methyls blue so they'll stand. Okay, and then the front carbon is attached to the back carbon. What's attached to the back carbon? 2 hydrogens and a methyl. Okay, if it was something else, you would write it. So if it was a chlorine, if it was a bromine, if it was an ethyl, you would write CH2, CH3. Okay, all right, so here they are. And so draw one Newman projection. Draw the one that you think is the lowest in energy, because I'm pretty sure that's what's behind that white box. Which one do you think will be lowest in energy? Most stable. Okay, so I'm going to write that over here too. Lowest in energy equals most stable. So we'll talk about the most stable conformation for this compound. Okay? All right, so is this what you drew? Okay, this is our Newman projection. Where is the front carbon that we're citing down in this picture? It's right here at that intersection. Oh, hang on, I need a pen. Here, we'll make it a different color. Right there. That's my front carbon. That's this one. Okay? Which one is my back carbon? It's the big circle. That's the back carbon. It's red. Okay? So the front carbon is attached to the back carbon, but what else is attached to the front carbon? 2 hydrogens and a methyl. And the back carbon has 2 hydrogens and a methyl. Okay, so now you see where they are. Here's the back. 2 hydrogens and a methyl. The front one, they're here. Now, did anybody do this and get it right? Okay, I want you to tell me why you picked that one to be the most stable. Because the methyls are farthest away from each other. It's like that obvious. Okay? They're farthest away from each other. So that's this one. Okay, so if I say, what is the name of that conformation? Which one is it? It will be, it's staggered. That's true. What else is it? Anti. Okay, so there's going to be multiple staggered ones, and some will be lower in energy than others, or higher in energy than others. Okay, so there's going to be like a range now because we changed our little hydrogens out. Okay, so this is going all the way around. Okay, we're going all the way around. All right, so here's the first one. Now, when you do this for a molecule, what works the best is to hold one carbon still and move the other one. Okay, do you see if you start doing this, it gets like uber confusing, like it isn't now? Okay, so I'm going to hold the back one still, and I'm going to take the front one, and I'm going to uchi it at 60 degrees. Okay, remember last time we were staggered eclipse, staggered eclipse. Look what happens on this one, the same thing. We're going to be staggered eclipse as we go around. My personal recommendation is that you start at one extreme or the other. Okay, and when we get to the picture, that is the reason to do that. Okay, so we're starting at anti, which we already said is the most stable. I'm going to turn the front carbon 60 degrees. So what do I get? B, which is eclipsed, right? So this is anti-staggered. This one is eclipsed. Okay, now I'm going to move it some more. We got to go 360 degrees to go all the way around. So when I move for C, I am once again staggered, right? But what else am I? What is the other word? What are these two methyls to each other? What degrees? Gauche. Very good. Gaucho. All right. Now I'm going to go to D. So I'm still moving the front carbon only. I'm holding the back one. You could hold the front one and move the back one. Just be consistent in your drawings and you'll be fine. All right. So here I go. And what am I again? I am eclipsed. And do you see that this eclipse is actually different than this one? Because what's in front of what here? Down on the bottom. A methyl's in front of a methyl. Up here, the methyl is, up here it's in front of a hydrogen, and this one is behind a hydrogen, okay? So that's why we call this totally eclipsed. That's like an annular, no, eclipse. Okay, so now what am I doing? I'm still holding the back carbon. I'm still going clockwise. So now what happens? I'm what now? I was eclipsed, so now I am staggered. Okay, and what is this one called? Say who? Gauche. Gauche. We're gauche. Okay, and then what happens? I'm what again? I'm eclipsed again. And then when you do the last turn, you end up back at A. Okay, now I labeled them with alphabet letters because I didn't want to redraw them on my potential energy diagram, which is where we're going next. Okay, so that's how come the letters are there. Okay, so we can do our potential energy diagram. Okay. All right, so we're going to draw the potential energy diagram for the conformational analysis of butane. Okay, we're going to start with A. Okay, so I'm going to draw an A up here. First of all, you have to have what? 2 axes. Okay, don't forget your axes. And then what is this one labeled? And what's this one labeled? Okay. You got that? Was that already on there?
Yep.
Gosh, and here I thought I was such a great teacher. Okay, so we're going to write on here. I guess I'll use the black. Maybe that'll work good. I'll make it a little thicker. Okay, now I'm going to put A on the scale. Okay, there's no number. Okay, where do you think it should be? High? You think it should be low? You think I should put it in the middle? What are y'all thinking? Low. Why? Because it's anti and it's staggered and it's the what in energy? The lowest one of all those pictures, right? So we're going to put A down here. Okay? We're going to take A and we're going to go 60 degrees and we get to B. Okay, B is what? Eclipsed, okay? So where do you think I should put B? About that?
Sure.
You like that? Okay. B is higher in energy than A. Do you all agree?
Yes.
Okay. All right, now we're going to go to C. C is also staggered, but it's not anti. It's gauche. So where do you want to put C? In between A and B. Okay, so I'm putting C there. See how we did that?
Yes.
Okay. Everybody agree with that? It doesn't matter, you know, I mean, as long as everything fits on your scale, we're fine. All right, now what about D? D is what? Total eclipse of the sun. Okay, so where do we put D? Above B. Does everybody see that? D is higher than B. Okay, where are you going to put E? What? Even with C. Does that make sense? Okay, so we're going to go to, I think I might have a slide that has it nicely on there. Okay, where does F go? Even with B. And then where did we end up? Back at A, which of course should be even with A. Okay, now I'm going to connect them with a lovely little line, okay, or a curve. So here we go. Okay, your curve is probably drawn nicer than mine, but it should be symmetrical. You see that? See how it's symmetrical? Okay, it doesn't matter if you start at A or D, but it should be symmetrical. Okay, that's why I recommend you start at an extreme, either the highest energy one or the lowest energy one. I think the book did it by starting at the highest energy one. Okay, so their picture looks a little different, but everything is C and E still match up, all that stuff. Okay, but it's split. Okay, because they went low, then went high to low, and then low back up to high. Okay, everybody got that? Is that too bad? Just a matter of practice. You got to practice drawing those Newman projections. I don't know why they like it. See, I thought I did have a really nice one for you. There you go. Okay. Look at that. I worked hard on that. Okay. The destabilization that results from atoms being too close together, that's in the eclipsed conformations, is often referred to as van der Waals strain, okay? And sometimes we'll use the term steric hindrance, okay? So what do you think would happen if I put something on here that's bigger than a methyl group? So let's put some more carbons on this guy. Okay. Okay, so I put 3 carbons on here. Okay, what is this group? If you're just talking about that group, what is that called? A T who? What? A T-butyl group. Okay, I'm gonna put T-butyl group over here. Now I'm leaving that blue carbon in there because I think it helps you see what's going on. Okay, and remember that each one of these methyls has what coming off of them? 3 hydrogens that I didn't put in there. Okay, look at this puppy. What do you think about this? We're playing Rock'em Sock'em Robots here. Okay, so they are totally running into each other. Okay, so what do you think that's going to do to this conformation? Make it very unstable. So what do you think that means about this one? Quite a bit more stable. Okay, so as these groups get bigger, the differences between the eclipsed and the staggered get greater. That makes sense. Okay, see, Rock'em Sock'em Robots. That's the key. Okay, you're all gonna be writing on the test, I know. Okay, what about anti versus gauche? Okay, here's the anti. So what do you think about that one? There's the gauche one. Yeah, it's still gonna be destabilized, but the anti is way more stable because we're keeping these big, bulky T-butyl groups far apart from each other as we can get them. Okay. Okay, identify the most stable conformation for butane. Let's see how fast we can do it. 26, right? Already did it, right, Jessica?
Yeah.
Okay. Woohoo! It's anti, right? Anti is going to be the most stable conformation. That's this one. Where the groups are as far apart from each other as possible. Okay? Like, should I put that question on the test? Okay. As we get into bigger and bigger alkanes, which is sort of happening here, they start to adopt a conformations where the hydrogens, 2, 4, 6, are all anti to each other. There's a blue carbon in there, but that's okay. So notice we have 2 up, 2 down, 2 up, 2 down, 2 up, 2 down. That's because if you look down every one of the bonds, okay, each one would be staggered, okay, and anti. So this and this are anti to each other. This is just big, okay? It's got 3 carbons, but it's anti to the methyl up here. You go to the next carbons, it's the same way, okay? So draw the most stable conformation of hexane in a Newman projection, sighting down the C3, C4 bond. Okay, so what do you do to start? Like, how do you start drawing that thing? What would you do to start? I'd start with a circle. Start with a circle. I'm going to put hydrogens on here while you attempt to draw it, and then I'll draw it. And I'll show it to you in this thing. Okay, in the meeting on Wednesday, I neglected to mention that Dr. Smith is buying us pizza. So you get free pizza. My last free hydrogen. And when you write your Newman projection, y'all, you should have all the carbons in it that are in the molecule. Okay, don't leave some off. Okay, because, I don't know, you thought they were assumed or something like they're not. Okay. Okay, so if it's hexane, you should have how many carbons in your picture? 6. Okay, all right. Here is hexane. Everything is staggered. That's the most stable. But we're going to sight down bond C3, C4. So I'm going 1, 2, 3, 4. So that's this one. So 3 is the blue one. Okay? So the blue carbon is the front carbon and the black one is the back one. Black back. Okay, wait. I was going to try to write on here with chalk. It doesn't work very well. I have enough issues. Okay, so here's my back carbon, and here's my front carbon. Okay, right there, that intersection, that's the blue carbon. Okay, what's attached to the blue carbon? 2 hydrogens. And what's this? A carbon, and what's on it? And a methyl. Okay, what is on the back carbon that I'm holding with my hand? That's the back carbon. What have we got up here? 2 what? 2 hydrogens. And what's down here? The ethyl. So make sure that you have 1, 2, 3, 4, 5, 6. Those are the 6 carbons. Okay? Now you're going to have some practice in going between the different kinds of pictures. Okay? So for example, hey, I think there's a way that I can ooh, look at there. Okay. So for example, if I have name that. Do you think I'm a crazy person? Okay. So what you should do is redraw it in a form that you understand, but you have to go between the forms. Okay? So what do we have here? We have a carbon, and what's attached to it? A CH3. And what's up here? Okay, and then we've got a H. Okay, and that's bonded to, make it big. Okay, the back carbon. Okay, what's attached to that? Oh, my bad.
2 hydrogen.
That was my bad, sorry. Didn't notice I'd missed it. Okay, and a CH3. Okay, now can you name that? So if you couldn't name this, could you name this? Please don't say no, I might cry. So what do you do first? Number 1, find the longest chain, which is how many? Does everybody agree that that's the longest chain? Okay, so your base name is? Okay, and then what else we got? A methyl, and which way do you want a number? It doesn't matter, it's going to be 3 either way, agree? So it's going to be 3 hyphen methyl pentane, all one word. That's a swoopy connection. Okay, there's also going to be some that you're going to practice in the homework where you have two compounds and you have to decide if they're the same or not. Okay, are they the same? Are they constitutional isomers? Are they stereoisomers? Oh my God. Okay, so what I recommend is usually one's in drawn one way and one is drawn the other way. Put them in the same form, and that usually makes it easier to tell. Okay, do it very carefully. Do it very slowly. Okay, you don't. I mean, I don't expect you to look at that and be able to name it. It took me years of practice to be able to do that. But you should be able to redraw it in a form that you're more familiar with, and then, okay? Okay, we got some fun stuff on Wednesday. We're gonna flip our chairs. Woo woo! I can't wait. I'm like so excited. We're gonna flip our chairs.
Oh, goodness.
See, I showed up again.